Bluware has more than 35 years of history for delivering innovation. As of now, we have more than 60 very talented consultants, which ranges from data scientists to software developers to SMEs, the geoscientists, and the project managers. So these multidisciplinary teams provide the staff augmentation to the projects where clients run the project, and we provide the competency. At the same time, there are several clients who come to us with a business problem, and we take their business problem, translate into a technical problem, and we develop solution from POCs to a production-ready TRL9 solutions. And when it comes to the solutions, we are working at a wide spectrum of different solutions to accelerate the development for your cloud journey, as well as to operationalizing your heavyweight machine learning models. The Bluware has the technology stack that we use in our services projects to build things in weeks and months rather than spending times in years. So what we call this, that's the product integration services, where we take one or more components from the Bluware technology stack to create an end-to-end solution, especially in the cloud environment. We have one piece of technology which is called the VDS, which is the foundation, which provides the foundation as the data format in most of our implementation. We have FAST, which make it possible to stream data instead of copying all the time when you take data from one workflow to another workflow. We have interactive AI as part of the Bluware technology stack, which is a deep learning framework for doing seismic interpretation. And last but not least, we have the Bluware engine, which provides an efficient way of working with the VDS data. It provides the necessary visualization that is required in the different parts of the workflows, and it provides the compute engine, which is the most important thing here, is to take all those models, the heavyweight models and algorithms, and optimize it for the parallel processing in a GPU environment. So the Bluware services take the challenge from their clients, and then to see which component of this Bluware technology stack can help to accelerate the development. Along with using our own technology stack, we provide comprehensive software development services, which from creating POCs to creating a TRL9 production-ready solution, to going back from implementation to the actually building those good AI models. We have another division in the Bluware services which provide the R&D services, and here the clients come with a challenge, and we have multidisciplinary teams who develops concepts and methods which can then be implemented as a solution. There are mainly 4 expert domains that this multidisciplinary teams are working on. First is the data science. This is the AI team that we have, and it focuses both on the symbolic AI and sub-symbolic AI. So your traditional machine learning and deep learning application, as well as creating reasoning engines or more physics-driven AI. At the same time, we have another group, which is the scientific computing group. So this is the group which specialized in numerical modeling and computational physics. So this group develops solutions around simulation for the HPC, for creating visualization solution, and also what cannot be achieved by the sub-symbolic AI, for example, for quantifying uncertainties and the other things which can support the solutions which are developed in the machine learning aspect. We have a team of software developers, both the front end, back end, and the DevOps, and this team works on developing more on the software development side, where we work on creating from POCs to TRL9 solutions. And the solutions we develop is both as in desktop applications as well as the cloud, the solutions on the cloud. So in next few slides, I will show you a few use cases where we worked with these clients for solving some complex problem. The first example I have is more on the operationalizing the machine learning model. So you have a heavyweight model, and if the end user wants to execute this model, this specifically model is for the seismic interpretation. If you see the workflow required to execute the machine learning model for doing seismic interpretation, the whole workflow is fragmented. There are a lot of intermediate steps that someone need to do before that job is being sent on the machine learning model. The data will come from somewhere, so there is a data access challenge. That data need to be converted into a format which is suitable for the machine learning application. While this conversion, data need to be QC'd. When the data is QC'd, there is also possibility that the source of data is not just the SegWi, but might be the data coming from different application databases. So to accessing the application database is not very straightforward, and it's a time-consuming process. When all this data is collected in a form that can be used or consumed by machine learning model, this whole data need to be managed as well. If there are 5, 10 cubes, it's easy to manage, but when it goes to hundreds of different cubes, then it is a big job to actually manage that data, so that can be effectively used to consume in the machine learning model. So this is more or less what is required from the data management side when you want to use the machine learning model for doing the seismic interpretation. But if you go to the to the machine learning aspect of the seismic interpretation, that's also not just a very simplistic workflow. What you have to do is that when the end user start to configure a job for machine learning, the first thing they do is that to find the best data which is suited for that specific use case. So finding data from hundreds of different cubes is not very straightforward. Even if they get the best data, that data need to be pre-processed in a way that can be efficiently used by the machine learning model. So, and most of these pre-processing workflows comes in the form of scripts. Although the end users intended for using this model are the geoscientists, so they're required to have skills around scientific programming and understanding the Jupyter Notebook environment, and the similar case is for the pre-trained model. So even if they get the pre-trained model, that usually comes in a Jupyter Notebook environment, so it's not very straightforward, especially for the geoscientists, to configure this model as well as tune the hyperparameter. They need to find which line in the code have to be changed if they want to change a parameter. So this everything is in the Jupyter Notebook environment, not very convenient for the end user, which is a geoscientist, to use this workflow. And afterwards, what they have to do is to configure these jobs, and these are the heavyweight models. So this is not going to run on a single machine, so they need to find some computational resources, and if everything is in the on-prem environment, it's really difficult to find resources. And we have seen some cases where it was almost impossible to run those jobs just because of the lack of the computational resources. Then the inference is done, it's also extremely important for end users to do the post-processing part, to actually get the best inference out of the machine learning model. That's again comes in the form of a scripts, which geoscientists are not very used to. And all this workflow requires some sort of visualization inbuilt somewhere, so they can look at what the output of the pre-trained model is, and how the inference look like, and different options that they have for the post-processing side. So all of these, there is a strong requirement to have an inbuilt visualization to visualize the different outputs within this workflow. So this whole workflow is fragmented. Everything is in the Jupyter Notebook environment, so there is no user-friendly way for end user to actually execute these workflows. What we came up with for these two clients is to create an end-to-end cloud-based solution for operationalizing this heavyweight model. What this solution had a data management component where we built it first a connector app which connects the on-prem storage as well as the storage underlying the GNG application to the cloud storage. So what this connector do is to transfer data to the cloud storage which have to be consumed by the machine learning model. The other thing, that component we built within the data management side, is the data conversion tool. Because we work in a VDS environment, which is the most appropriate environment that you can get if you want to use your seismic data and consume it in the machine learning model. But most of the time, the data that we get access to is not in the VDS format. So what we did in these implementations, we created a data converter tool within the same environment, which can access SegWis and the other legacy format from the on-prem sources as well as from the GNG databases and convert it into VDS and upload it into the scalable cloud storage. And during this conversion, there are two more things happening. The first thing is that when this conversion happens, we built it in integrated visualization capability, so that each time the SegY is converted into VDS, the end users who are doing this conversion can visualize that data straight away to make sure that the conversion has gone right. At the same time, when this conversion happens, the data is uploaded into the cloud storage, it's registered as a data catalog. So, and this data catalog is then afterwards used to find the data from thousands of different cubes. On the machine learning side, what we did is that we took this heavyweight pre-trained model and refactored those models as a Bluware engine plugins. And these plugins made it possible to optimize the execution of those workflows for parallel processing in the GPU environment. And and then we built a very user-friendly interface where end users, which are the geoscientists, can access the system through a web portal and execute the whole workflow. And that, when it says the executing the whole workflow, that means they can create new seismic interpretation projects. They can find the best suited data for running the machine learning models. They can QC it within the inbuilt visualization. And when they are satisfied with their input data, they send this input data to the machine learning model, and here they have a library of different machine learning model. They can choose the appropriate model, they can choose the appropriate hyperparameters, and then the job is sent to the Kubernetes cluster. And this is for this cycle, we use another piece of technology, which is the scale out, which take the computations from one node and scale it up to the Kubernetes cluster. When the jobs are done, they have the inbuilt visualization, which they can use to QC the inference. And if they are satisfied with the inference is, or the predictions, that is then realized back to the cloud storage, which is then connected, take it back to be fed into the other GNG application. So this whole workflow is integrated from data conversion to finding data for running machine learning models, to creating inference and then feeding inference back to the other parts of the GNG workflow. The execution of these jobs is extremely fast because of, first, we have an optimized compute engine which is optimized for parallel processing in the GPU environment. The other thing is that now jobs are not running on one node, but instead of running on the Kubernetes cluster. And we have a piece of technology which connect all these things together, so the jobs are distributed in a Kubernetes cluster, and when the inference is ready, this inference is taken back and stitch everything back together that they can visualize it and realize it into the VDS, inference VDS, and then it converted back to fed it to the other parts of the GNG workflow. It's a very user-friendly. This system is designed for geoscientists, not for a software developer. So they can do the whole workflow in a very user-friendly way. So what it provides is that a completely integrated framework where you can execute the whole workflow within minutes rather than spending weeks and months to be stuck in the different parts of the workflow. So this is an example of where we took an AI model which is developed in R&D, and we developed an end-to-end cloud-based solution. Let's take a step back, and I'll show you a couple of projects where we work with different clients to actually build those models. So this is what we are doing in the R&D part of the services. There's one example here, and when you see the performance of the AI model, it's highly dependent on the complexity of the subsurface. If the subsurface features are simple, or what I say, the complexity of the subsurface is rather simple, then most of the time our AI models works very fine. But it's a very different scenario if we have a complex features in the subsurface. So this is one of the challenge given by one major E&P company who came to us to say and explained that okay, so we have an AI model. It works very fine with a simple geology, but we are not looking for a simple geology. We are looking for a specific complex geological features, which were more on the channel mapping, which is a pretty hard thing to do, and the shallow hazard. So the challenge was given that can we do something to improve the prediction accuracy? Now, improving the prediction accuracy, there can be two things that someone can do. The one is the model-centric approach, where you build more sophisticated pre-trained model, or maybe the retrain model a lot so it can perform better. But if statistically speaking, you can expect to have an improvement by 3 to 5%. The other thing that you can do to really improve your prediction accuracy is to work on the input and output of the model. So if you precondition your data in a better way, or you transform your input data in a way that it is easier for machine learning model to find those features, that can make a huge difference. And on the output side, it's all about the post-processing. You have a better workflow which remove false positive, for example, in a better way, you can expect to have significant improvement in what you can image in the subsurface. So this was the challenge given to us, and what we did, it was an R&D activity, and in this R&D activity, we developed a custom workflow for each application which was targeted in the project, and we managed to get the channels out from using the machine learning model in a very efficient way. Another challenge in this situation that the AI model and the workflow was working in the isolation. So there was an AI model which requires an input and output, but this input is coming from another part of the workflow, and the output is being fed to another part of the GNG workflow. So there is having these things in isolation was a big hurdle. So what we did in this specific project is not only finding a way to create best prediction, but also we developed a Petrel plugin. And that Petrel plugin, what it do is that to streamline and seamless integration from where you can get data, you can process that data in your machine learning model, and then it is seamlessly integrated into the other parts of the workflow. So this is an example where it's more of the creating a way of getting better prediction than just the implementation. And this is where we managed to get quite very extremely good structural and stratigraphic interpretation of the subsurface. So, which is extremely important in the prospect evaluation. But along with the structural interpretation, there is another thing which is extremely important when it comes to going for drill and drop decision. That's the reservoir properties. And the reservoir properties, the main thing is the porosity and permeability. And how do we do in a conventional workflow is that we have seismic inversion data that we used to estimate the porosities, and then we derive permeability from that porosity. So that's a very well-established workflow, but if you see the performance of this workflow, that is not very optimal. In this specific use case, the average match between the porosity estimated by the seismic inversion with the actual porosity encountered in the well was 71%, and 1% change in the porosity means 1% change in the volumetrics, because it's directly related to the volumetric. So it was extremely important to have a good certainty that the porosity estimation was correct before the drill and drop decision has been taken. So we were given challenge that can we come up with a new optimization algorithm which can take the information from the seismic inversion and can improve the performance and break the barrier that we have for the 71%. So this is an example of symbolic AI or physics-driven AI, where we didn't use the machine learning, but we developed a custom algorithm which takes this data and try to improve the spatial distribution of porosity, and then use that porosities to derive permeability. And in this specific use case, where the average match was 71%, we were able to have a match of 87%. So from going from 71% to have a match of 87%, that is an extreme improvement. So this was an R&D project, not around the machine learning, but the symbolic AI part. Again, the same challenge is that, okay, we have developed a method, so what? If the end users can actually not use it in a user-friendly way, then the whole effort spent here is gone. So what we did that at the end of this project, we took this optimization algorithm and we created a simple backend and a front end, a tool where again the end user can execute these workflows in the language that they speak, in the way that they are used to work. So these are the two R&D projects. One is more on the sub-symbolic AI side, and the other one is in the symbolic AI. I have one more example to show you, which is again going into the R&D part, is the fact that although we call it that neural network produce probability as their output, but in the reality is that if you want to use this probability to put a cutoff to say yes or no, it's easy. But if you want to use those probabilities values itself, it's not very straightforward, because those probabilities are far from the realistic probabilities. Because the way neural network works is that it's always skewed towards the end. It always skewed towards the extreme. So it either try to close to the zero, or it try to get close to the 1. So the actual probabilities values is very difficult to use in this situation. So we were given a challenge that the client wanted to use these probabilities for uncertainty quantification. So it's not just that your network tells that there is a fault, but they also wanted to know that what is uncertainty in these predictions. So that was a complex problem, because this is a generic limitation in neural network. So what we came up with is, of course, looking into the latest research and then try to see that how we can use that research and repurpose it for seismic interpretation. And this uncertainty comes in the, so one thing that I have explained is the generic limitation in neural network that is skewed towards the extreme ends. But if you take one model and you run the same data set 3 times, it's quite possible that you get slightly different results. Now, which you cannot explain, because you are using the same labels, you are using the same data set and same AI model, but you are getting different results. So objective on this project was that, okay, how we can actually use all this information to generate an additional information is not just the yes or no, but also the how confident that model is in terms of the prediction. So in this project, we created this, developed this an R&D workflow by using several methods. For example, temperature scaling to bring back those unrealistic probabilities to more realistic probabilities, as well as we created an ensemble method where you run, for example, you get 10 realizations for a same model with the same data set, and then you try to see how different your predictions are. So, and then we created a way to translate that information into uncertainty. So not only you get that if you have your fault or not, but also you get information about the uncertainty in the how do the model see. So these are the few examples from creating new methods to actually taking the internal R&D in operators and then implementing it into a production-ready solution. So just to summarize, there are 3 things mainly we covered. We used the Bluware technology stack to not only develop the solution, but also to accelerate the development and to achieve the performance criteria defined by these clients. We developed custom solutions which do not have any component from the Bluware technology stack, but more focused on the conventional software development. And third thing that I explained is the R&D to actually push boundaries of what is possible with the state of the art of AI, and then to see what else we can achieve.